Hello and welcome back to the video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 37 in the series, Multiplying Polynomials. So as indicated in this video, we're going to investigate the multiplication of polynomials. Essentially, this is just going to boil down to the distributive property, since all we're going to be doing is multiplying sums together. When you multiply a sum, you need to multiply each term in the sum by whatever you're multiplying by. And that might, in turn, require the distributive property again. Once we get done with that, we'll be grouping like terms, which, again, is the distributive property, as we've seen. And so it's really going to rely on this one particular property. And so it's probably best if we begin by recalling that property. Notice that when I have a sum, like b plus c, and I want to multiply it by a, I can do that. I don't have to do the b plus c first, even though it's in parentheses. What I can do is multiply each term, both b and c, by a. And that's actually good for just the simplest polynomials, like if I want to multiply a binomial by a monomial. But what if a is another binomial? Or in other words, what if a wasn't just a single number, but was a sum itself? This was the situation we looked at previously where we developed foiling. If I want to, I can first distribute the entire a and b term both against c and against d. That would look like this. Then I could distribute again, now the c into the a plus b term, and also the d into the a plus b term. And we would get the following four terms. Now, it didn't matter if we went a plus b and distributed that first, or if we took c plus d and distributed that first. We would still get these four terms. And the most common way, I think, to get those four terms that we're taught in school is using this FOIL acronym to make sure that we get all four of them. We have the first, a and c, we have the outer terms, a and d, we have the inner terms, b and c, and we have the last terms in each sum, b and d. That lists all the possible combinations. Now, one thing to notice here is that order really doesn't matter. You could distribute, right, and get your last terms, and then your outer terms, and then your inner, and then your first. It doesn't really matter in what order you get these four things. It just matters that you get these four things, right? Addition is commutative, so this sum could be written in any order and still give us the right stuff. It's worth noting at this point, it also doesn't matter in which order we wrote the a plus b versus the c plus d. If I switched these two, that's also fine. So any order that we could write it in, taking advantage of the commutativity of multiplication and addition, is fine. Another way to think about this, which is going to be interesting in terms of thinking about how polynomials work with counting, the number of ways of doing something later on, is to notice that really what we've done is we've paired up every combination of elements from the first parentheses with elements in the second parentheses. Elements in the first parentheses were a and b, and we paired up a with c and a with d, both elements of the second parentheses, and b with c and b with d. So we took each one from the first parentheses and paired it up with everything from the second parentheses. And so both foiling and the distributive property, these are just tools that help us remember to get every combination every time. All right, let's look at how this would apply to some polynomials. Here we have the binomial x plus 2 and the binomial x plus 6. What happens when we multiply them? Well, first, x times x, that's x squared. X times 6, that's 6x. 2 times x, that's 2x. And 2 times 6, that's 12. Now, when we do some polynomials, we'll often have like terms that we can collect. If I collect the 6x and the 2x together, I get 8x. And so we wind up with this trinomial, x squared plus 8x plus 12. It's only got 3 terms, but that's because 2 of the original 4 terms were like, and so we could add them. So just to reiterate, we started out with a sum of 2 things times a sum of 2 things, and we got 4 things. And it transformed into 3 things because of like terms. Once we were done combining, we got just 3 things, and hence this was a trinomial. Here's another example where things go a little bit differently. Let's say we had x squared plus 1, which is a binomial, and times that by x minus 1, another binomial. So we're going to wind up with 4 terms here. The first is x squared times x, that's x to the third. Then the outer term, x squared times minus 1, that's minus x squared. The inner term, 1 times x, here we have him, and 1 times minus 1, which is minus 1. Notice that none of these are like terms, and so we cannot simplify. This is where it ends. We don't go any further than this. So let's summarize what we've just learned with some critical notes. Copy this down, show it to me later so I know that you watched this video. If I FOIL these two things, I wind up with these four terms. If I FOIL these two binomials, I wind up with these three terms because the two terms bx and dx are like, and so we can just add their coefficients. Okay, so let's continue with multiplying some binomials together. Let's consider what happens when we change the sign of one of them. Here I've indicated the foiling I'm about to do, and here we get the terms as a result of that foiling. Notice that we now have two different signs, a minus 6x and a plus 4x is our middle terms. When we combine those, it looks like a difference, right? We have 4 and 6 with a difference of 2. That's just because the 6 was negative and the 4 was positive. And when we add negatives and positives together, it looks like a difference. Here's a slightly spicier one. Let's take a look at this. At the very least, I've put parameters in each place instead of numbers here. And what's going to happen? Well, we're still just going to FOIL. And there's even less to do because I don't have any numbers to carry out the arithmetic for. Our first terms is ax times cx, that's acx squared, because there's two x's. And then I have the outer term, ax times d. So that's just a times d times x. Then I have the inner term, b times cx. That's bcx. And then I have the last terms, b times d. We're still just foiling here. I still have like terms, like that previous example. The adx and the bcx are like terms in terms of x, so we factor that out. And I have the following, acx squared plus ad plus bcx plus bd. We're going to look at a lot of things like this, so let's get kind of used to this idea. Maybe pause the video here if you like and try to FOIL this. I've indicated the foiling elements. So for our first terms, we should wind up with 3x times 2x, that's 6x. Then 3x times minus 1, that's minus 3x. Then minus 2 times 2x, that's minus 4x. And minus 2 times minus 1, that's positive 2. Our like terms combine, and they're both negative, so minus 3x minus 4x is minus 7x. Each of the four original numbers are all contributing to the numbers in each one of these three terms in the final trinomial. This pattern is important. It's important enough that I want you to write it down in your critical notes. What does it look like when we multiply two general linear terms together? We get the following. So what about multiplying polynomials with more terms? We looked at a lot of binomial multiplication, two terms times two terms. But what do we do if there's more terms in each polynomial? How do we handle that? Well, we're still going to just use this idea. We don't have foiling anymore. The acronym doesn't hold. There's more than four terms. But we're still going to just apply the idea that every term in the first polynomial needs to multiply by every term in the second. So for example, here I have x plus 2 times 3x squared plus 2x plus 1, a binomial times a trinomial. And I need to take my x, and I need to multiply it not just by 2 this time, but 3 terms. And I need to take my 2 and also multiply by these 3 terms. Now, two things I'd like you to note. Number one, we're going to have 6 terms to deal with. There's 2 here, and each one multiplies by 3, so I get a total of 6 terms. Now, those terms might collapse. I like to stack my like terms like this. So we take x and multiply by 3x squared, we get 3x cubed, 2x, we get 2x squared, and 1, we get x. We take 2 and we multiply it by 3x squared, we get 6x squared, 2x, we get 4x, and 1, we get 2 when we multiply 2 and 1 together. So now what I've done is I've written it this way where the like terms are already stacked. Because now when I add them, it's easy to see who pairs with whom. And when we do that, we get 3x cubed, because there's nothing to pair with this guy. This turns into an 8x squared, this turns into a 5x, and this turns into just a 2, because there's, again, nothing to pair it with. So this is our final answer. And it has less than the original 6, because 2 pairs of them collapse down into single terms by like terms. So I think this is a really good idea. Try to stack your like terms when you do these big polynomial multiplications, because that helps you keep track of who's going to add up with whom. So let's look at one more example. Let's look at a trinomial times a trinomial. And here I've chosen these powers so that we're going to have some interesting cancellation of like terms. But we still just are going to take each one of these and multiply it by every term in the second polynomial. Let's begin with the x cubed. X cubed times x to the fourth is x to the seventh. X cubed times minus 2x squared is minus 2x to the fifth. And x cubed times minus 6 is minus 6x cubed. Now let's move on to the times 2x. So the 2x times x to the fourth, that's going to be 2x to the fifth. 2x times minus 2x squared is minus 4x cubed. And 2x times minus 6 is minus 12x. Moving on to the last one, we have 1 times these terms. So this is just x to the fourth minus 2x squared and minus 6. Notice I've tried to stack them in a way where the powers line up, because this tells me who I need to add up with whom. Notice also that I have 9 terms because I had 3 terms in the first times 3 terms in the second gives me a total of 9 terms. How do they cancel? Well, I have x to the seventh dropping down, minus 2x to the fifth, and 2x to the fifth is just 0, so we don't even write it. X to the fourth comes on down, minus 6 and minus 4 is minus 10, x is to the third, minus 2x squared has no partner, it comes on down, same thing with minus 12x, same thing with minus 6. So here is our final answer. That brings us to a critical example. I want you to copy this down as a good example of a trinomial times a trinomial. I'm doing x squared plus 2x plus 3 times 3x squared plus 2x plus 1. We begin with x squared times everything in this second parentheses. This is going to be 3x to the fourth for x squared times 3x squared, 2x to the third for x squared times 2x, and x squared itself for x squared times 1. Then we move on to the 2x. 2x times 3x squared is 6x to the third. 2x times 2x is 4x squared. And 2x times 1 is 2x. Then we move on to the 3. 3 times 3x squared is 9x squared. 3 times 2x is 6x, and 3 times 1 is 3. Notice that I've stacked them by their powers so that I can add up my like terms easily. 3x to the fourth has no partner. 2x to the third plus 6x to the third is 8x to the third. X squared plus 4x squared is 5x squared plus 9x squared is 14x squared. 2x plus 6x is 8x, and 3 has no partner, we drop it down. So here is our final answer. Notice that 3 terms times 3 terms gave us 9 terms, but a lot of them stacked with each other, and so we only had 5 terms in the end. Finally, let's consider multiplying polynomials by themselves. Let's consider the positive integer powers of polynomials. So remember, all positive whole number powers can be thought of as repeated multiplication. So for example, I could think of x minus 2 squared as x minus 2 times itself. We FOIL, we combine like terms, and we get x squared minus 4x plus 4. Likewise, if I wanted to think of 2x plus 1 to the third power. This is 2x plus 1 times itself, 3 times in total. Let's FOIL the first term, and after collecting like terms, we'll get 4x squared plus 4x plus 1. Then let's distribute this trinomial against the terms in the second parentheses. Each one in the first must multiply by each one in the second. So for the first one, I'm going to have 4x squared times 2x, which is 8x cubed, 4x squared times 1, which is 4x squared. Then 4x times 2x, which is 8x squared, plus 4x times 1, which is 4x. And finally, we have 1 times 2x plus 1, which is 2x plus 1. By stacking, I group my like terms automatically, and then we add everything up to get our final answer. Okay, that's it for the notes. Let's try some praxis exercises. Pause the video at this time and give these a shot. Okay, let's see how you did. So for the first two, let's see, I had x plus 1 times x plus 2. We FOIL, we collect like terms, and you should get x squared plus 3x plus 2. Same with this one. Notice that I kept the numbers the same here. I'm just sort of changing the signs. I wrote this in a slightly different order, but that doesn't matter. Multiplication is commutative. So what do we get? We expand, multiplying each one in the first parentheses by each one in the second parentheses to get 4 terms. Then we collect like terms, and this is our answer. Moving on to these two, again, we FOIL and we collect like terms. Number 4, we FOIL and we collect like terms. Notice that even though all I changed in 1, 2, 3, and 4 were which ones were positive in the constant term and which ones were negative, we wind up with some similar related answers about what the last ones were. See if you can start to pick out a pattern of the pluses and minuses and whether or not the middle term is a sum or a difference. Okay, so how do we attack trinomial on trinomial? We get each one in the first, and we multiply it by each one in the second. Here I did x squared first. That gives me 2x to the fourth minus 4x cubed minus 5x squared. And then the 3x times each one, that's positive 6x cubed minus 12x squared minus 15x. And then finally, we've got 1 times this, so we just copy this down, and now we're going to group like terms. So by stacking them this way, we group like terms easily, and then adding up all of these coefficients, with sign, we get the following. 2x to the fourth plus 2x cubed minus 15x squared minus 19x minus 5. So that's it for the standard notes for today. However, if you want some supplementary notes talking a little bit more about polynomials, here we go. Polynomial multiplication is one of those patterns that sort of encodes other mathematical features in the pattern of its multiplication. This gives us a backdoor to look at other math problems. Let's see an example of this. Specifically, we're going to look at how combinatorics, which is the mathematics involving counting up the number of ways that things happen, is also part of polynomial multiplication. To see this, all we have to do is look at Pascal's triangle versus expanding the binomial x plus 1. Pascal's triangle, we get each next row by sort of adding up the things which are diagonal to it above. 1 plus 1, for example, is 2. 2 plus 1 gives us this 3. 3 plus 3 gives us this 6, and so on. And it turns out that Pascal's triangle gives us the numbers, called the binomial coefficients, which tell us how many ways we can draw a certain number of things from a collection of things. Let's take, for example, this 6 right here. There are 6 ways of drawing 2 things, so this is 0, 1, and 2 things, from a total of 4 things. So if I had 4 people and I wanted to know how many groups of 2 I could make, the answer is 6. And I want you to notice that these numbers in this triangle, they pop up when we do this kind of foiling exercise. If I go through the effort of multiplying out x plus 1 to some power, and you can try this for a few powers of n, it's not too hard. If you have n to the 0th, well, that's just 1. Anything to the 0th power is 1. If you have to the first power, it's itself. The second power, you should be able to do this one easily, and I even think you should be able to do the third power pretty easily using this video. You'll wind up with these coefficients. And notice how they're mirroring the Pascal's triangle coefficients. And here also we have n equals 4, same thing. So what's happening here? Well, it turns out that there are 4 different ways that this product is going to turn into a square, or a cube, I mean. There are 6 different ways in which this product is going to give you terms which turn into a square. And so there's a way in which this foiling action is related to counting. So just to sum it up, if you take a look at the 6, this is the number of ways of choosing 2 things from a group of 4 things. And that happens to be, for very specific reasons, the coefficient of the x squared term. And so there's this relationship between counting and the coefficients of polynomials. I don't want to go into a great deal more detail than that. I really just want to point out that one of the reasons that we're interested in polynomials isn't just because they're cool to assess and model real-world problems. They do that too, but also because their multiplication is intrinsically tied to combinatorics and the mathematics of counting things. So you also have a use for polynomials in that regard. Okay, that's it for this video. Thank you very much for your patience and have a great day. Good luck with your studies, and I'll see you in the next one.